My name is João Vilela, and I'll be presenting a model of transmission expansion planning under uncertainty. I'll be doing a comparison between multi-cut and single-cut benders decomposition. I'm doing that based on the Lumbreras, Ramos, and Sanchez article published on 2014. So what's a TEP problem? A TEP problem, which is a transmission expansion problem, it aims to provide decision support to system planners concerning new installation of equipment. So basically everything they need to add to an existing grid in order to attend future load. Currently, we are seeing a lot of renewable energy coming in, and they are volatile and uncontrollable. So that's a source of uncertainty. And also, there's a lot of uncertainty towards load growth. So state-of-the-art models, they have to contemplate uncertainty to properly represent real dynamics of the system. For large problems with thousands of buses and hundreds of scenarios, the traditional TEP models, they become computationally untreatable. Therefore, we are going to use Bender's decomposition that have resources to solve large-scale problems such as this one under uncertainty. So what we want to do here is to use Bender's and compare single cuts and multi-cuts and see the impact on performance and solution in general. So let's look at a basic TEP model. So here we have two parts of the objective function. The first part is the decision of investment. So there's a cost of investment and there is a binary option of investment, or I invest in building a circuit, or I don't invest in building a system. The right side is basically minimizing dispatch. So you want to attend loads with your generation at minimum cost. So basically here we are deciding if we need to add circuits to the grid in order to properly attend this load with the current generation that we have. The right side of this problem right there, you can see kind of a trick to use this binary decision. There's an M, which is a big M times 1 minus X. That's the decision of allowing a circuit to exist. If that holds, then the circuit exists and the flow is properly calculated. Otherwise, it doesn't, and the solution does not contemplate this circuit. So that's the idea. So the model that I presented, all of the subscription that we need and the information that we need about this model is here. So when we go to the stochastic model, we only add uncertainty in the format of scenarios. So here we are adding W, which represents a scenario. So basically what changes is the second part of the objective function, which is the dispatch. So basically you're continuing to use only one decision, or I invest or not invest, and contemplating several dispatch scenarios. So as we can see here, it changes the behavior of scenarios of dispatch that are being contemplated. And for the model that I just showed, that's all of the parameters that we will need. Here I want to highlight the dual variables that we are going to use for benders. So I want to talk a little bit about them. So we are going to focus on the pi and the whole. The pi represents the dual for circuit capacity constraints, both positive and negative. And the whole represents the duals for the 6-second Kirchhoff laws. both positive and negative as well. We are going to use it later. So what's the challenge here? We have large size problems that lose performance and become untreatable as they grow. Furthermore, uncertainty on load and renewable energy require more scenarios to fully represent them. This makes the problem too big to solve on traditional ways, and then we use benders to actually tackle the problem. Also, we can explore here two different techniques, the single cut and the multi-cut techniques, so we can kind of explore how they affect performance and solution in a general form. And with that in mind, that's what we will do on the following slides. So just looking at the single cut approach, we are going to look at a TEP problem on the following way, with the first stage and the second stage. So the first stage here I present in the general format, but the first stage we are looking at only investing or not investing in circuits, and the second part of the first stage is the theta, which has linear constraints associated with it that should be responsible to approximate the second stage function, cost function. So that's the idea here. The single cut approach seeks to get an approximation based on the average of duals that are relevant to the first stage, and the average of optimal operation costs that comes second stage costs that comes from second stage. So we look at the first stage, we solve the first stage, we carry the optimal solution from the first stage to the second stage. We solve it several times according to the number of scenarios, and all of these solutions will give us the duals and the optimal costs. So the single cut will get the average of the optimal costs and the average of solutions, and we will use that as a constraint on the first stage scenario, on the first stage problem. When we look that in our problem, and when we transfer that to our problem, the first stage becomes the investment, so investing in circuits, right? And here we see the expression on the first stage that represents the linear approximation of the future of the second stage costs based on the average of the duals that comes from the second stage and the average of optimal costs. So here we only have one theta, so that's the idea, right? And we will do exactly the same thing. So we invest, and with the optimal decision of the first investment, we send this to the second stage, which is the operation. So we do several different operations according to different scenarios, and this will give us different duals and different optimal costs, and we take the average and take it back to the investment stage, and then we do that until we accomplish the precision that we want on the solution. When we go to the multi-cut approach, what differs here is that instead of averaging the optimal costs and averaging the duals, we take every single dual and optimal costs from the problems that we solved, and we create constraints for every one of them. So here we have more constraints to approximate even better the optimal the second state cost function. So that's the idea. Uh, but the bad side of this is that you have a even bigger problem as the first stage. So if you have, for example, 200 scenarios that you're contemplating, for every iteration you're sending back from the second stage to the first stage 200 scenarios. And also you have on the first stage, instead of only one theta, you have one theta for every scenario. So you're approximating every scenario, the functions of every scenario, and taking the average of them, and that is how you contemplate this on the first stage. In the same way, when we look at our functions and our problem, we maintain the same structure, but instead of taking back from the second stage to the first stage the average of duals and optimal cost, we take everything. So we take every duals for every scenario, for every iteration, and every optimal cost for every scenario and every iteration, right? Until we attain the criterion of tolerance. So how are we going to do that? We are going to use Julia programming language. We use express.jl, which is an interface to the Express solver. It solves linear and nonlinear convex problems. In our case, we have linear and an integer problem. So that's okay. It can solve our problem. And we also use JUMP, which is a domain-specific modeling language for mathematical optimization. Just a glimpse of the solution. We are going to first look at a case study of a really simple case study of 5 buses, 3 generators, and 2 demands. We also have 3 candidate circuits that we can evaluate if we need to build them or not. We are also assuming that we have a penalty for deficit in order to avoid deficit, and it's a really expensive penalty, 5 million. And also the big M, we are setting it to 10 to the 4th in order to solve it. So when we look at the grid, here is the information about the circuits, the buses, the generation, and the demands. And also in red here on the bottom right, we have the information about the circuits. So basically, what comes as we solve this problem, it's a really simple problem, and the decision is to invest this line from 2 to 3 right here in red, in dense red. So why did it decided to invest in it? So basically it comes and this will bring a little bit of intuition on how it solves this. So basically it comes from the second stage, which aims to minimize the dispatch costs. So what happens here is, if you take a look at the demand, so we have their great values of demand, and those values of demand, they force the dispatch of generator 1. So why am I saying that? Because as we want to minimize generation cost, we want to first dispatch energy with the generator that is cheaper, right? So in this case, G4 is cheaper, and then G2, and finally G1. So, but we have scenarios that demand more energy than G2 and G4 can provide. Therefore, G1 has to dispatch. And to properly dispatch and attend demand, the model saw that it was necessary to build the line from 2 to 3, so it could properly attend demand and it wouldn't pay the penalty of deficit. And in the end, the cost of investment was the cost of the circuit, which is $14 million. And then we go to a real case. So this is the real deal. So we got this case from PDE. It's a Brazilian real case. And we will use it to further understand, so that we can have a deeper understanding of Bender's approaches and impact on solution, right? So here we have a 10,000 buses, 14,000 existing circuits, 2,000 candidate circuits, more than 1,000 generators, from hydro plants to thermal plants to renewable plants, and 3,000 loads. So this is a huge case. It's really hard to solve this case. Traditional models cannot solve this type of problem easily. So here it's valid to clarify some things as well. So for simplification purposes, we set hydro and renewable power as thermal plants with cost 0, because it's water, wind, and sun. It doesn't have an associated cost along. So as a way of simplifying, they were modeled in this way. The uncertainty that we will be contemplating here is related to load, only load. So here we have a variation of load for every one of the buses, and when we sum them up for every single scenario, we see how volatile it is. So we have really different magnitudes for every one of the scenarios, and for each scenario we have a specific distribution of loads for every single scenario. So that's what we are looking here. We are looking also at 24 scenarios that will be contemplated in total. And here, as I said, we can look at the density. So as we can see here, we have different magnitudes for every single scenario and different distributions. So that will give our case a really notion of how demand can vary. So, and we will be able to see how that impacts the decision of investing in new candidates. So one thing that I should say and didn't say before is that the case that I got was the case of 2029, which was the last configuration that the planner publishes. So in theory, this case should be able to hold every single needs of the system on the last year. And as we will see further, if we apply this kind of variance to loads, the system will need more reinforcement. Okay, so first we will look at the convergency, so we can start to explore the impact of benders and single cuts and multi-cuts on the solution. Here we vary the types of cuts, the tolerance, and the number of scenarios, and we evaluate the solutions based on iterations, the time that it got, and if it were able to converge or not. So that's the idea. And the things that were really interesting from that result were the following. So first, the gap. When convergency was achieved, it was below the smallest tolerance. So in this case, 0.001% for all of the tests of 12 scenarios. So that implies very similar times of solution for all of them, because they were able to achieve the optimal solution on the smallest tolerance on the same number of iterations. So that's why they take the same time to solve. We see a little bit difference on multi-stage and single stage, but not too so significant. And in this case, all of them converged. So, one interesting thing it was that the multi-cut approach, it did not converge for the 24 scenario tests. Even if we relax the tolerance to 0.01%, it didn't converge. The smallest gap that it was able to obtain was 1.7%. So really high value and way above the greatest tolerance that we tested here. So that's interesting. And even more interesting was that the single cut for the 24 scenarios was able to obtain optimal solution and convergence with one less iteration than the 12 scenario. So probably as it is seeing more scenarios than the 12, it was able to approximate the operation costs function on a better way, on a better manner, and it was able to achieve convergency earlier. So here we just take a look at the convergency graphs. So as we can see and expect, they are slowly coming towards the optimal solution, both for multi-cut and for single cut for the 12 scenario tests. For the 24th scenario tests, we see that the single cut was able to achieve optimal solution, but as we discussed before, the multi-cut did not achieve the tolerance that we wanted, so it was lost, and it wasn't able to achieve. So concerning investment analysis, we can see that the models they basically gave us 4 circuits that should be part of the expansion. So those are the following circuits. They are all 500 kV of operational voltage level, and they are located close from each other. So here, when we consider the test case of 12 scenarios, single cuts and multi-cuts, they gave us the same solution, but they gave us 3 lines, the first 3 lines. But when we look at the 24th scenarios, the single cut gave us 3 lines, but the multi-cut that didn't converge, it gave us 4 lines. So that's interesting because it brings out how important is to adjust the tolerance. So the tolerance in this case have a really high impact. So if we were to accept the 2% tolerance, the multi-cut for the 24 scenarios would be okay, and then the last circuit would have been built. So that is 77 million that would have to be added to the investment cost, which is a lot. In a real case, that should be avoided as maximum as possible. So this is interesting because it's associated with a real dynamic of the system that is expected to happen even more significantly in the future. So we have a lot of renewable energy coming up on the northeast region, and all of that energy should flow to the southeast region where the load is highly dense and concentrated. So the fact that all of the lines were built on the state of Bahia and have high capacity of power transfer, it shows us that all of that energy that's coming from the northeast, uh, it has to have ways of flowing from the northeast to the southeast. And the interesting about Bahia is that Bahia is the frontier between the northeast and the southeast. So the fact that the circuits are located there show that what the model has in mind is that the decision is a need for reinforcement of the interconnection between the northeast and the southeast to support uncertainty on demand, especially on the southeast. So that's a really interesting result. Finally, what we can take from all of this presentation is that the Bender's decomposition methodology with single cut and multi-cut presented itself as a relevant approach towards solving a large-scale transmission expansion problem, especially under uncertainty. So that's really good. Otherwise, we wouldn't be able to solve this problem. For an increase of scenarios, a single cut outperformed multi-cut as convergence problems started to appear for multi-cuts. So that's relevant as well. Concerning computational performance, no significant difference was found for convergent solutions, in this case from the tests of 12 scenarios. So basically it was at the same time of performance, it wasn't different. So no significant difference was found. And finally, the investment decision followed a rationale that makes sense, which is really good, proves that kind of validates the model and proves that it can brings a lot of insightful information towards the decision that system planners have to have. So that's it. Thank you for listening to this presentation. I hope you enjoy.